Hello, I am Christopher McLatchy, and in this video I'll be covering the topic of solving boundary value problems with linear dielectrics. In the case of a homogeneous isotropic linear dielectric, the bound charge density is related to the free charge density as described by this equation. Therefore, when there are no free charges embedded within the material, the potential fits Laplace's equation, and separation of values can be used to solve for the potential. The free charge on the surface of the dielectric can be described using these equations here. Now, because the potential should end up being a continuous function, we know that the potential directly above the surface of the material should be equivalent to the potential directly below the surface of the dielectric. Now, in problem 4.22 in Griffith's textbook, we are given a scenario in which a long cylinder of linear dielectric material is placed within a uniform electric field E0 that is perpendicular to the axis of the cylinder. The cylinder has a radius of A, and the material has a susceptibility of chi sub E. We are asked to find the electric field that is produced within the cylinder. These are the boundary conditions that we will be using to solve for the potential. Boundary condition 1 comes from the continuity of the potential that we addressed earlier. Boundary condition 2 comes from this equation here, as there are no free charges in the problem. Boundary condition 3 comes from the fact that the uniform electric field that the cylinder is placed in is not affected by the cylinder at a distance far away from the cylinder. Now, by using separation of variables, you should get this general equation here. To find the potential, all we need to do is solve for the coefficients. For the potential inside the cylinder, B must be 0, as the function will blow up at the center of the cylinder otherwise. Therefore, we can describe the potential inside the cylinder with this equation. For the potential outside the cylinder, A must be 0, as the function won't converge otherwise. We also need to consider that the potential should converge as dictated by boundary condition 3. This gets us an outer potential described by this equation here. Using boundary condition 1, we get this equation, which can be expanded like so. To make this equation a little nicer to look at, I had to find the products of the coefficients as shown here, which simplifies the equation like this. From this equation, we can define a set of equations that demonstrate the relationships between the coefficients. Using boundary condition 2, we can obtain this equation. This equation can be expanded to look like this. From this equation, we can obtain another set of equations to further describe the relationships between the coefficients. Now, by using this equation and this equation, we can obtain this equation here. And by using this equation here and this equation, we can obtain this equation as described here. Now, if g sub k is any value other than 0, this means that epsilon over epsilon naught is equal to -1, which is impossible. Therefore, g sub k must be equivalent to 0. Now, if we use this equation here with this equation, we obtain this equation, which, if you notice, is the exact same. It has the exact same issue as we had up here, and thus h sub k is equal to 0 as well. Now that we have defined our coefficients, let's return to the equation we obtained for the potential within the cylinder. After we expand the function like this, we can plug in the values that we found for the coefficients, which results in this equation here. Now, assuming that the potential at the center of the cylinder is 0, we find that G naught is 0, which gives us this equation. This equation can be made a little nicer by acknowledging that the distance from the axis of the cylinder multiplied by the cosine of phi gives us x. This results in this equation here. Now that we have the potential for inside the cylinder, we can find the electric field inside the cylinder using this equation, which results in 2 times epsilon naught times E naught divided by the sum of epsilon and epsilon naught. And finally, by using the definition of the permittivity of the material, we end up with this equation. Because we set the vector E naught pointed in the x direction, we can define the equation like this. And what is interesting about this equation is that it demonstrates that the field within the cylinder is pointed in the same direction as the field that the cylinder was set in. The inner field just has a smaller magnitude. And that is all I have regarding this topic. Thanks for watching.